Everything you've been told about light is wrong, not incomplete, not simplified, wrong. You think light is a wave? Right. You think it's a particle? Also right. You think that makes no sense? Now you're getting it. In the next 45 minutes, I'm going to show you what light really is, and I promise reality will never look the same. Let me start with something simple. Look around you. Everything you see, this room, your hands, the screen in front of you, you're seeing it because of light. Light bounces off objects, enters your eye, and your brain constructs an image. Easy, right? But here's the thing. What is light? Not what does it do, not how does it behave. What is it? You were probably taught in school that light is a wave, like ripples on water. It has a wavelength, a frequency, it diffracts around corners, it interferes with itself. All the hallmarks of wave behavior, and there's mountains of evidence for this. Young's double-slit experiment in 1801 proved it beyond doubt. Light is a wave, case closed, except then came the photoelectric effect. Shine light on a metal surface and electrons pop out. That's strange enough. But here's the truly weird part. If you increase the brightness of the light, you don't get faster electrons. You get more electrons, but each one has the same energy. If you want faster electrons, you need to change the color, the frequency of the light. That makes absolutely no sense if light is a wave. A bigger wave should carry more energy, but it doesn't work that way. Einstein looked at this in 1905 and said something radical. Light isn't a continuous wave. It comes in chunks. Little packets of energy he called photons, particles of light. And he was right. He won the Nobel Prize for it. So light is a particle. Case closed, except we already proved it's a wave. So which is it? The answer is going to break your brain, but in the most beautiful way possible. Let me show you the experiment that destroyed our understanding of reality. It's called the double-slit experiment, and it's so simple a child could set it up. But what it reveals is so profound that even after 100 years, we're still arguing about what it means. Here's the setup. You take a light source, doesn't matter what kind, a laser works well, and you shine it at a barrier with 2 narrow slits cut into it. Behind that barrier, you put a screen that lights up when photons hit it. Now, if light is made of particles, little bullets of energy, what should happen? Well, some particles go through the left slit, some through the right slit, and you get 2 bright strips on the screen, like throwing sand at a wall with 2 openings. Simple, but that's not what happens. Instead, you get a pattern, multiple bright and dark bands, an interference pattern. The kind of pattern you only get when waves overlap. When a crest from one wave meets a crest from another, you get brightness. When a crest meets a trough, they cancel out. Darkness. This is exactly what happens when you drop 2 pebbles in a pond and watch the ripples interfere. So clearly, light is a wave, the 2 slits create 2 sources of waves, and those waves interfere. Beautiful. Classical physics. No problem. But wait, what if we turn down the intensity of the light? Way down. So far down that we're sending 1 photon at a time. 1 single particle of light. Now there's no way for waves to interfere. There's only 1 photon. It either goes through the left slit or the right slit. We should get 2 strips, but we don't. Even sending photons 1 at a time, waiting seconds between each one, the same interference pattern builds up. Slowly, photon by photon, each one landing in a seemingly random spot. But over time, the pattern emerges, the same pattern we got when we treated light as a wave. How is that possible? How does 1 photon, 1 single particle, interfere with itself? Is it going through both slits at once? You know what? Let's check. Let's put a detector at each slit, something that clicks when a photon goes through. Then we'll know. So we set up the detectors, we run the experiment again, and the interference pattern disappears. Now we get 2 strips, exactly what you'd expect from particles. The moment we try to find out which slit the photon went through, it stops behaving like a wave. It chooses 1 slit, goes through, and acts like a sensible particle. But if we turn off the detectors, if we don't look, the interference pattern comes back. The photon knows whether we're watching. Let me say that again. The behavior of light changes based on whether we're measuring it or not. That is not a metaphor. That is not an interpretation. That is what happens in the lab, every single time. And it gets worse. All right, let's back up. Maybe we're thinking about this wrong. Let's go back to Einstein's idea. Light comes in photons, discrete chunks. Each photon has an energy that depends on its frequency. High frequency, like blue or ultraviolet light, means high-energy photons. Low frequency, red or infrared, means low-energy photons. That explains the photoelectric effect perfectly. When a photon hits an electron in a metal, it transfers its energy. If that energy is high enough, the electron escapes. If not, nothing happens. Doesn't matter how many low-energy photons you throw at it, none of them individually have enough punch. Turn up the brightness, you're just sending more photons. Each electron still only absorbs one photon, so you get more electrons ejected, but each one has the same energy. Change the color, the frequency, and now each photon has more energy. So each electron comes out faster. Perfect. Physics saved. Except we still have the interference pattern problem. If photons are particles, how do they interfere? Here's where we have to make a conceptual leap that's going to feel insane. The photon doesn't go through the left slit. It doesn't go through the right slit. It goes through both. Not in the sense that it splits in half. In the sense that until we measure it, the photon exists in a superposition, a combination of all possible states. The photon is neither here nor there. It's in a state of potential. It has a certain probability of being at the left slit and a certain probability of being at the right slit. And here's the key. Those probabilities are described by a wave, a probability wave, specifically a quantum wave function. This wave goes through both slits. The wave interferes with itself, and where the wave has high amplitude, the photon has a high probability of landing. Where the wave cancels out, the probability is zero. So when we send one photon at a time, each photon's probability wave goes through both slits, interferes with itself, and the photon lands somewhere according to that probability distribution. Over time, as we send thousands of photons, the pattern of where they land matches the interference pattern of the probability wave. The photon is guided by a wave of probability, not a physical wave, not a water wave or a sound wave. A mathematical wave that tells you the likelihood of finding the photon at any given place, and when you try to measure which slit it went through, you collapse that wave function. You force the photon to choose. The superposition ends. The photon becomes localized. It's definitely at the left slit or definitely at the right slit. And now there's no interference, because there's no superposition. There's no probability wave going through both slits. The act of measurement changes the state of the system. This isn't a disturbance caused by clumsy equipment. It's not that we're bumping the photon with our detector and messing it up. It's fundamental to the nature of reality. Before measurement, superposition. Multiple possibilities coexisting. After measurement, one definite outcome. I want you to sit with how strange that is. The universe doesn't have a definite state until you look at it. Now you might be thinking, okay, fine, probability waves, superposition, I'll accept it. But why? Why does nature work this way? And here's the beautiful and frustrating truth. We don't know. We can describe it. We can calculate it with stunning precision. Quantum electrodynamics, the theory I spent a good chunk of my life developing, can predict the behavior of light and electrons to 10 decimal places. It's the most accurate theory in the history of science. But why it works? That's a different question. What I can show you is a way of thinking about it that I find deeply satisfying. It's called the path integral formulation. Here's the idea. When a photon travels from point A to point B, say from a light bulb to your eye, you might think it travels in a straight line, the shortest path. That's what we teach in school. But actually the photon explores every possible path. It could go straight, it could curve left, it could loop around the room 17 times and then arrive. It could bounce off the moon. Every path, no matter how absurd, contributes to the final probability of the photon arriving at point B. Each path has an associated probability amplitude, a complex number, and you add up the amplitudes from all paths. The square of that total gives you the probability. Now here's the trick. Most of those crazy paths cancel each other out. The path that goes left interferes destructively with the path that goes slightly more left. The loop around the room cancels with a slightly different loop. What survives? The paths that are close to each other and reinforce. And it turns out, Those are the paths near the classical straight line. So in everyday life at human scales, light looks like it's traveling in straight lines. But fundamentally it's not. It's a sum over all possible paths. And in situations where multiple paths can contribute significantly, like going through two slits, you get interference. The path through the left slit and the path through the right slit both contribute. Their amplitudes add up, and depending on the relative phase, whether they're in sync or out of sync, you get constructive or destructive interference. That's where the pattern comes from. The photon doesn't choose a path. It takes all of them, simultaneously, in superposition, and when you measure which slit it went through, you're forcing the photon to commit to one history, one path. The superposition collapses. This isn't mysticism, this is mathematics, precise, predictive mathematics. But I'll be honest with you, even though I can calculate it, even though I've spent decades working with these equations, I don't truly understand it. Nobody does, and that's okay. Nature doesn't owe us intuition, it just is what it is. Let's go deeper. You know what color is, right? Red light, blue light, green light, different wavelengths, different frequencies, but here's something strange. A single photon doesn't have a definite color until you measure it. Let me explain. A photon can exist in a superposition of different frequencies. It's not that it is red or is blue and we just don't know which. It's genuinely in a combination of both states. Only when you measure its frequency, say by passing it through a prism or using a detector tuned to a specific wavelength, does it choose a color. Before that, it's a blur of possibilities. This applies to everything: position, momentum, spin. All quantum properties exist in superposition until measured. There's a famous thought experiment called Schrödinger's cat. You've probably heard of it. A cat in a box with a radioactive atom. If the atom decays, it triggers a mechanism that kills the cat. If it doesn't decay, the cat lives. Quantum mechanics says that until you open the box, the atom is in a superposition of decayed and not decayed, which means the cat is in a superposition of alive and dead. The moment you open the box, the wave function collapses, and the cat is definitely one or the other. Now, Schrödinger proposed this as a criticism. He thought it was absurd. Cats aren't both alive and dead. That's ridiculous. And he's right. At the scale of cats, superposition doesn't happen. The cat interacts with air molecules, photons, the walls of the box. Those interactions cause decoherence. The superposition is destroyed almost instantly. But at the scale of photons and electrons, superposition is real, measurable, undeniable. The double-slit experiment proves it. And here's the thing that bothers people. If a tree falls in the forest and no one is around to hear it, does it make a sound? Quantum mechanics says the tree is in a superposition of fallen and not fallen until you look. That sounds insane, and maybe it is, but it's what the math says, and the math works. Now let me show you something even stranger. Two photons can be entangled. Here's what that means. You create two photons in such a way that their properties are correlated. For example, their polarizations are linked. If one is polarized vertically, the other is polarized horizontally. But remember, before you measure them, they're in superposition. Neither photon has a definite polarization. Now you separate them. Send one photon to a lab in New York, the other to a lab in Tokyo. You measure the polarization of the photon in New York. Let's say you find it's vertical. Instantly, and I mean instantly, faster than light could travel between them, the photon in Tokyo knows to be horizontal. Einstein hated this. He called it spooky action at a distance. He thought it violated the principle that nothing can travel faster than light. But experiments have confirmed it. Over and over, entangled particles really do exhibit this correlation, no matter how far apart they are. How? Because they're not two separate particles, they're one quantum system. The wave function describes both photons together. Measuring one collapses the wave function for both. It's not that information is traveling from New York to Tokyo. It's that the information was never localized in the first place. The two photons are part of a single non-local quantum state. This breaks our intuition about how the world works. We think of objects as separate, independent things, but at the quantum level, that separation is an illusion. Everything that has ever interacted is, in some sense, still connected. The universe is deeply, fundamentally interconnected in ways we're only beginning to understand. So why should you care? Because this isn't just abstract theory. This is the foundation of reality. Every technology you use, computers, smartphones, GPS, medical imaging, depends on quantum mechanics. The transistors in your computer work because of quantum tunneling. Lasers work because of stimulated emission. MRI machines work because of nuclear spin states. None of this would exist if we didn't understand quantum mechanics. But more than that, this changes how you see the world. You are made of atoms. Those atoms are made of electrons and nuclei. Those electrons and nuclei obey quantum mechanics, which means at some level you are a quantum system. Your particles have been entangled with particles across the universe. The photons hitting your eye right now have taken every possible path to get there. The atoms in your body exist in superposition until they interact with their environment. You are not separate from the universe. You are a pattern of quantum fields, temporarily localized, briefly coherent, part of an unimaginably vast and interconnected whole. And when you look at the stars, the light that enters your eye left those stars years ago. It traveled through the vacuum of space, went through both slits if you put up a barrier, existed in superposition the entire time, and then, at the moment it hit your retina, it collapsed into a definite state. You didn't just see the star. You participated in the star's quantum event. That photon's journey doesn't end until you observe it. In a very real sense, the universe doesn't fully exist until it's observed. Not by humans specifically, by anything, a detector, an atom, anything that causes decoherence. Observation isn't magical, it's just interaction, but it's fundamental.
So what is light? It's a wave, it's a particle, it's a probability distribution, it's a quantum field excitation. It's all of those things and none of them. Our language fails us because our language evolved to describe the macroscopic world. Trees, rocks, water, things that are definitely in one place at one time. But light doesn't care about our language. It does what it does, and what it does is beautiful. It interferes with itself. It takes every path. It connects distant parts of the universe in an instant. It refuses to have definite properties until forced to. It reminds us that reality is stranger, richer, and more mysterious than we could have imagined. I've spent my entire life studying this. I've won prizes for it. I can calculate things about light that no one else can, but I still don't really understand it. And you know what? I'm okay with that. Because the joy isn't in having all the answers. The joy is in asking the questions, in seeing the pattern emerge, in feeling that shiver of awe when nature reveals something unexpected. Light is impossible, and yet here it is. You're seeing it right now, and that's the most amazing thing of all.